Welcome back. Today's video is on section 5.2 in your pre-calc textbook. We're on page 357. Today we're going to talk about verifying trigonometric identities. Now we want to talk about the word verify. To verify means to affirm or confirm that something is true. So we're going to affirm the truth value. Why is this important? Well, we're going to be continuing to simplify expressions. We're going to be working with equations, making the left look like the right. You are not allowed to, at the end of your work, declare that the statement is false. That's not the goal here. The statement that's given to you is true. You must demonstrate your affirmation of that truth value. Please bear that in mind as we work through the examples and checkpoints together today. I draw your attention to page 357. There's a box on that page. It's got 5 items in it. And I want you to look at item number 5 first. It's really the most encouraging statement in the whole box. It says, always try something. Something. Even making an attempt that leads to a dead end can provide insight. So these problems don't always have an obvious path. We're going to work through checkpoints. We're going to give you some pointers about how to proceed. But again, every problem is different. They're like little puzzles. We're going to be, again, working the left to the right. We're going to oftentimes start with the most complicated side and try to simplify it using the tools that we learned in the preceding section. Sometimes, although this is my least favorite, sometimes we have to change both the left and the right so that they equal each other, but they look entirely different than the original problem. So let's get started. Let's see what we can do with this today. Moving over then onto page 358, if you would like to follow along, you'll notice again, the directions say verify the identity. So let's take a look at checkpoint number 1. Checkpoint number 1 says sine squared theta plus cosine squared theta divided by cosine squared theta secant squared theta equals 1. I would say the left is by far more complicated than the right, so let's see what we can't do with the left. Well, again, using the Pythagorean substitution, sine squared plus cosine squared simply equals 1. Likewise, secant squared theta. I've got a cosine sitting next to it. Let's use the reciprocal identity, 1 over cosine squared theta. So now in this overall denominator, I have cosine squared theta over 1 times 1 over cosine squared theta. Well, that's of course going to be 1 over 1, which is 1, and we've met the goal. We verified the truth value of the equation. We've effectively made the left look like the right. Let's move on. Let's take a look at another one. In checkpoint, for example, number 2. This time we're working with cosecant squared. That's a beta, by the way. That's a Greek letter beta. We don't often use it, but we need to get used to that. You'll find it in physics. You'll find it in calculus. So we certainly are going to get a little bit of experience working with the beta variable. So here we have 2 cosecant squared beta equaling this time 1 over cosine beta plus 1 over, 1 minus, let's fix that. That would make that a very different problem. Let's see, 1 minus cosine beta plus 1 over 1 plus cosine beta. Now again, noticing that the denominators are different, we worked with this in the last section. This side more complicated than this, so we're just going to hold this constant. We're going to work strictly with the right. The LCD here, of course, is going to be the product of 1 minus cosine beta and 1 plus cosine beta. So, having that product in our denominator, noticing then in the first term we are lacking 1 plus In the second term, we are lacking 1 minus cosine beta. Of course, these are each multiplied by 1, which were the numerators that we started with. Then combining like terms, the cosine betas cancel, 1 plus 1 equaling 2 over 1 minus cosine squared beta. Again, Pythagorean substitution would tell us that 1 minus cosine squared beta is simply sine squared beta. Well, reciprocal identity would suggest that if I think of this as 2 times 1 over sine squared beta, that sine squared beta in the denominator really is what? Cosecant squared beta. So once again, I now have 2 cosecant squared beta equaling 2 cosecant squared beta. And I have affirmed, I have verified the truth value of this statement. Again, we worked with the right because the right was more complicated than the left. So this again is following the instructions that were back on page 357. Keep trying something. So far we've been working with the more complicated side. On the top of 359, I draw your attention to the top of that page. The Pythagorean identities have been restated for us in their original forms. And you'll notice there's kind of a V scenario, giving you what's called the equivalent forms. The algebraic manipulation of the Pythagorean identities will be very, very helpful. You'll notice that we've solved for sine squared, we've solved for cosine squared, and we've also manipulated with secant squared, tan squared, cosec, and cotan. Again, memorizing these patterns and understanding the algebraic manipulation of these is extremely important. We're going to use these as our helper as we move into checkpoint number 3. Checkpoint number 3 says we've got some Pythagorean expressions that we're going to need to manipulate. Here we have secant squared x minus 1, and we have sine squared x minus 1 equaling the opposite of sine squared x. Well, let us use those equivalents that we found on the top of 359. We know that the first one, secant squared x minus 1, is simply tan squared x, and that sine squared x minus 1 is negative cosine squared x. Again, these are being multiplied. This is the sign, it's not a subtraction symbol. Well, once again, let's use then a quotient identity. Tan squared x is sine squared x over cosine squared x minus, here we go, multiplied by minus cosine squared x over 1. Then we can cancel common factors. We have a negative 1, and we have a sine squared x, which is exactly what we had on the right. So again, we've verified the truth value of the statement using multiple equivalencies of the Pythagorean identities. The left far more complicated than the right, so that's where we started our work. Moving on then, let's take a look at example number 4. This one, not so obvious. What is more complex, the left or the right? Which one is worth starting with? Well, sometimes, again, we take a stab at it and see what's going to work. In checkpoint number 4, we have cosec x minus sine x equaling cosine x and cotan x. I'm going to go ahead and start on the left, and the reason being, this is a binomial. These have differing trig values, but at least they are considered a singular expression with 2 factors. On the left, I have a little bit more going on. So in this case, I'm going to begin by rewriting cosec as 1 over sine x minus sine x over 1. The good news here is now I have express both of these in terms of the same function. Going to build an LCD, going to multiply, of course, then by sine x. So here I'm going to come up with 1 minus sine x squared all over sine x. Again, that was me doing this. When I simplify here with the Pythagorean substitution, I have cosine squared x over sine x. So notice I've gone from a binomial to a monomial. Yes, it's a ratio, but I've made some improvements. Now let's take a look. Sometimes we're all about bringing things together. Sometimes it's wisdom to separate the two. So this time I'm going to take that cosine squared and I'm going to associate the sine x component to the denominator, to this factor, but I'm going to leave the other cosine x alone. Well, cosine over sine is cotan, and cosine, of course, is itself. Noticing here, of course, multiplication is commutative. So, in fact, I've made the left look like the right. I have verified the truth value of this identity. So one more time. I worked from the left first because it was a binomial. I was able to use a reciprocal identity so that I was working only in sine. I found the LCD. I then combined the numerator, used a Pythagorean substitution there. Then I was wise to split my fractions as I did because I knew what the goal was. I knew that this was really cosine over sine, so I said, well, let me take advantage of that. And again, using then the quotient identity, making the left look like the right. This is the checkpoint, for example, number 4. Over on page 360 then, it says at the top, recall from algebra, we talked about rationalizing denominators using conjugates. And I referred to those conjugates back in 5.1. We used conjugates to rationalize irrational real denominators. We've used conjugates to rationalize when we have complex numbers in our denominator, because again, that implies radicals in denominators, and whether the radicand is real or whether the radicand is imaginary, that doesn't fly. We're not allowed to have those. And so we rationalize denominators using conjugates. We're going to continue with that thought in this section. We're going to be utilizing conjugate pairs, binomial pairs, with, in fact, this time, the trig values. The goal, of course, ultimately being to somehow use some sort of then identity substitution to further simplify. So for checkpoint number 5, let's take a look at what we have to verify. Again, directions for all these are the same. Verify. This time we have cosecant x plus cotan x equaling sine x over 1 minus cosine x. So this time I have a binomial on the left in terms of 2 different trig values, but I have a ratio on the right, and that denominator in and of itself is a binomial. So I think this time I'm going to work on the right. I'm going to leave the left alone and see if I can't do something with this. The conjugate for 1 minus cosine x is going to be 1 plus cosine x. Again, conjugates, you know, the values are identical. The only distinction is the joining arithmetic symbol. So if we start with a subtraction, we change to an addition. Whatever we do then to the denominator, we're also obligated to do same to the numerator. Because other than the number 0, any number divided by itself equals 1. I'm creating an equivalent form, equivalent fraction. On the right-hand side, I have not changed the original problem whatsoever. So moving down then from there, I'm going to go ahead and distribute. So that's going to leave me sine x plus sine x cosine x all over 1 minus cosine squared x. Again, the beauty of this is that I know now I've moved into the Pythagorean identity mode, which is going to then be replaced with sine squared x. So I have sine x plus sine x cosine x. Much like we did in the preceding example, sometimes it's in my best interest to separate the denominator. But this time, I'm going to associate the denominator with both terms in the binomial. Over here, I had to make a choice. Because these were multiplied together, the sine x either went here or it went here. Because I am joined with an addition pattern here, the sine squared x belongs in both places. So now I have sine x over sine squared x plus sine x cosine x over sine squared x. Well, now I can simplify each fraction individually. That's a 1 and that's a 1, so that's 1 over sine x. Plus, again here, I've got this one. This is going to disappear, and I'm allowed to do that because these are multiplied. So now I have cosine x over sine x. Using the reciprocal identity, 1 over sine x is cosec, and cosine over sine is cotan. So now I've met the goal. The left looks like the right. I have verified the equality. I have affirmed the truth value. Again, choosing to work on the right first this time because we had a binomial denominator. Using its conjugate pair, multiplying both numerator and denominator, creating an equivalent form of the Pythagorean identity, which allowed me to create a substitution here. That took that binomial denominator and made it a monomial. Choosing to separate then and associating the same denominator with each of the terms from the numerator, I was able to simplify each fraction individually, using then a reciprocal substitution here, using a quotient identity substitution here to affirm the left equaling the right. This is checkpoint number 5. Moving on, we're almost done. Checkpoint number 6. Checkpoint number 6 says, well, sometimes we can't work on the left and make it look like the right. Sometimes we can't just work on the right and make it look like the left. Sometimes we have to work on both sides. Again, my least favorite, but sometimes these problems require that we do exactly that. If I take a look at the checkpoint for number 6, this time I have ratios on both sides. I have tan squared x, or theta, I suppose they've used, and that's over 1 plus secant theta. And this is equal to 1 minus cosine theta over cosine theta. So again, in this case, I have tangent, I have secant, I have cosine, I have a binomial numerator, I have a binomial denominator. I've got a lot going on here. So what I'm going to do is I'm going to attempt to simplify each side in hopes that we can find some rewrite on the left that's going to be in agreement with a rewrite on the right. So let's start with the left. Tan squared theta, using the Pythagorean equivalence, we've got we've got secant squared theta minus 1 now over 1 plus secant theta. Well, I love this. This works beautifully because this is the difference of squares. So this is now secant theta plus 1 and secant theta minus 1 all over 1 plus secant theta. Well, of course, addition is commutative. So we know that this binomial factor and this binomial are in fact equivalent. That yields secant theta minus 1. And right now I think that's a linear factorization. That's as far as I'm going to be able to take that one. On the right, however, let's take a look at what we've got going. Again, sometimes it helps to separate. And this is one of those times. So I'm going to make this 1 over cosine theta minus cosine theta over cosine theta. Again, because this is a binomial with a subtraction pattern, much like I separated in checkpoint 5 over sine squared x, I'm going to have to separate here, but I'm not associating cosine theta with one of the two denoms. It has to go with both. Then I'm going to use the reciprocal identity here because I know that 1 over cosine is secant. And of course, cosine over cosine is simply 1. So notice now I've made the left look like the right. Neither one of them look like their original. I had to rewrite in both cases, but in fact, I have verified the truth value of the equation. This is checkpoint number 6. Now, examples from calculus is the title of example number 7. I don't want you to be worried about it. The only thing that I can suggest to you is that we're using higher degree. We're just using higher degree. Everything we've done up to this point has been with respect to quadratics or linears, and we still can work with degrees that exceed 2. So our last example in this section is going to do exactly that. We're going to use the same practices, the same methods. We're going to be wise mathematicians just as we've been all along. And as item 5 in our list of suggestions states, always try something. So let's take a look at checkpoint number 7 together. Checkpoint 7 suggests to verify tan cubed x equaling tan x secant squared x minus tan x. Well, thinking as we did from the very beginning, the right-hand side looks far more complicated than the left. I have a monomial, and that monomial includes, that binomial on the right includes 2 different trig values. The monomial on the left, while it has a degree of 3, at least it's only in 1 trig value. So taking a look at the right, I notice I have a tan x and a tan x. That's a GCF as far as I'm concerned, so I'm going to go ahead and take that out. That's going to leave me secant squared x minus 1. Well, secant squared x, again, from the equivalent for the Pythagorean substitution, we know that that's tan squared x. So now I have a tan x and times a tan squared x. Now, we haven't talked a whole lot about this, but you know that if I had, for example, a to the first times a squared, laws of exponents would suggest that that's a to the 1 plus 2, or a cubed. Well, that law of exponents still applies here. This is really tan x to the first. This is really tan x to the second. We write it this way. Notice that tan squared x is equal to tan x squared. But tan squared x does not equal the tan of x squared. I think it's important to understand this. It's kind of like a PEMDAS issue. In this case, this would suggest that I would take the domain value x. I would apply the function to it. I would take its tan. And then I would square the outcome. Here, the suggestion is that I take the value x, I would square it first, and then I would apply the tan function. These are not the same things. So do be careful. You are very welcome to write the tan x squared in this format, being sure though that you put the squared component in front of the domain value. So in this case, it is as if I have a 1 here. So tan x times tan squared x is simply tan to the 1 plus 2, or tan cubed x. And isn't that what I was looking for all along? So this is checkpoint 7, letter A. We have a B. We have a second one to take a look at. Letter B says sine cubed x cosine to the 4th x equaling, and this is a mess. This is cosine to the 4th x minus cosine to the 6th x times sine x. Well, again, I think this looks a lot worse than that. I think this is far more complicated. So I'm going to work on the right and see if I can't make the right look like the left. Concentrating then on the binomial, I notice that I'm going to have a GCF and it's going to be cosine to the fourth. So I'm going to go ahead and take that out. And that's going to leave me 1 minus cosine squared. And still sine x being multiplied behind. Well, 1 minus cosine squared x, you know what that is by now. That's going to be sine squared x. And again, still times sine x. And bringing down from in front, cosine to the fourth x times sine squared. Well, just as we discussed over here with the tans, the same thing's going to be true with the sines. This is sine squared x, this is sine to the first together. That's going to give us the sine cubed x and cosine to the fourth x. We know that multiplication is commutative, so we have sine cubed x and cosine to the fourth x. We've made the left look like the right. We've verified the truth value of the statement. So we've now covered 7 example checkpoints. I'm doing the checkpoints specifically to give you additional problems to be solved. You can also follow Mr. Larson's steps for the example problems themselves. Now I'll draw your attention to the homework for the section that I've put up here on the board. We're going to split this video across 2 nights. Due this evening, the 25th, will be numbers 9 through 40 from section 5.2, pages 362 to 363. Then due tomorrow evening, from the 26th, numbers 41 to 46, and 59 through 52. Once again, if you are having difficulty, please enter your questions in the discussion for chapter 5 on my MySchool app page, and I will look at your questions and I will respond. But in the meantime, please be working daily and please be uploading your PDF homeworks to me so that I can be monitoring your progress. Okay, that's it. Thank you.